Hello world, it's Rahul. Welcome back guys to machine learning tutorial. So guys, today we'll see how to solve linear regression problem using Bayesian approach and what are their advantages over classical linear regression approaches. So guys, Bayesian versus frequentist debate is one of those academic arguments that I find more interesting to watch rather than engage in. So instead of taking one side, I think it's more productive to learn both methods of statistical inference and apply them wherever appropriate. So guys, as we have already solved simple linear regression problem by making use of least square error and gradient descent, let's quickly understand where our model is restricting in terms of using this approach for real world datasets. So guys, for understanding this, let's do a small thought experiment with regards to regression problem. Okay, let's take a coin flip example. So when we flip a coin, there are two possible outcomes, heads or tails, and we'll conduct a series of coin flips and record our observations, that is, the number of heads or tails observed for a certain number of coin flips. So guys, in this experiment, we'll try to determine the fairness of the coin using the number of heads or tails that we observe. So before going ahead, let's create some rule for this. So if we observed head and tail with equal frequencies, or the probability of observing heads or tails is 0.5, then it can be established that the coin is a fair coin. And if we failing that, then it will be a biased coin. Now let's say I flip the coin 10 times and I observe the heads 6 times. Then my probability value will be 0.6. Perhaps one of my friend who is not convinced and extend this experiment to 100 trials using the same coin, then he observes heads 55 times, which results in different p-value with 0.55. So guys, now we have two values of p with us, and after this, I am sure that you must have several questions with you, like how much confident are we of p being 0.6? How much confident are we of p being 0.55? If we have two p values, then which of these values is the accurate estimation of p? And if we go for further experiments, will p continue to change? So all I can say is that we cannot find out the exact answers to these questions using classical approach of solving linear regression problem, which means that this approach doesn't tell us that how much our model is certain to predict an output. And when we say certain, that means what is the probability of correctness what we have predicted as an output. Now just imagine a situation where your friend gives you a new coin and asks you for the fairness of the coin without even flipping the coin once. So by making use of your past experiences or observations, you'll expect the probability of getting a head as 0.5, as you already know that you have equal chances of getting either heads or tails. Now we have two case studies as shown on the screen. So case 1 will be observing 5 heads and 5 tails. It means we are with 0.5 probability. And case 2 will be observing h heads and 10 minus h tails, where h will not be equal to 10 minus h. So guys, if I talk about first method, what it suggests is we are using frequentist method over here, where we omit our beliefs when making decisions. However, the second method seems to be more convenient, as 10 coins are insufficient to determine the fairness of a coin. Therefore, we can make better decisions by combining our recent observations and beliefs that we have gained through our past experiences. So the mechanism which uses our most recent observations together with our beliefs or inclination for critical thinking, known as Bayesian thinking. Now let's extend this assumption. So now suppose your friend allows you to conduct another 10 coin flips. Then you can use these new observations to further update your beliefs. As you gain more data, you can incrementally update your beliefs, increasing the certainty of your conclusions. So guys, this process is nothing but known as incremental learning, where you update your knowledge incrementally with new evidences. So guys, by collecting this information, we can conclude the drawbacks of frequentist method over Bayesian approach, such as in Bayesian approach we involve prior knowledge to determine final outcome. Prior knowledge make it possible to incrementally improve the estimated result in new observations or evidence. And last but not the least is it adds ability into the model to express uncertainty during the time of model prediction. Now as we know the drawbacks of frequentist approach and introduced some new features as well using Bayesian approach for modeling machine learning algorithm, I'm still having one question, that is there any necessity of these new features, or what are their roles in enhancing the algorithm, as we were quite happy with the model outcome what we were getting from solving the linear regression problem using least square error or gradient descent. So guys, let's see why these capabilities are important in machine learning, especially in real world applications. So one of the major challenges in machine learning is to prevent the model from overfitting. Especially when we have a small data sets, the model will only learn the specific configurations of the given data that doesn't generalize to the unseen data. However, if we have beliefs that were gained through our past experience, those could be used to generalize our model in the absence of sufficiently large dataset. Therefore, with Bayesian learning, we can use such prior knowledge or beliefs to provide additional information to the model. Then recently, the scalability of machine learning algorithms to big data application has become a challenge due to limited computational resources. If a machine learning algorithms require a complete dataset to be available in the memory for the computations, then those algorithms will require a large amount of memory to scale them to big data applications. However, if a machine learning algorithm can inherently support incremental learning, then we can load a subset of the data into memory for computations in each increment. So guys, Bayesian learning can be used as an incremental learning technique to update the prior beliefs whenever new evidence is available. So again, here Bayesian learning is playing a crucial role. So guys, ability to express the uncertainty of prediction is one of the most important capabilities of Bayesian learning, even though uncertainty is underappreciated in machine learning. It has significant benefits to real-world applications. The uncertainty of predictions is an important concept when making decisions involved with high risk in industries such as financial and medical industries. Now, as we have clear understanding of why and where we should use Bayesian approach, so let's quickly see how we can implement Bayesian approach for solving linear regression problem. So guys, simple linear regression tries to fit the relationship between dependent variable y and single predictor, that is independent variable x, into a straight line. And as we know the straight line equation, that is y is equal to mx plus b, we'll rewrite this relationship as y is equal to wx plus tau plus e, as shown on equation 1. So guys, here tau is the intercept value and w is the slope value, and the term e represents the individual error when modeling real world data that doesn't fit perfectly to a straight line. Now we have to determine the values for these unknown parameters tau and w for minimizing the total error. So guys, one way of doing so is by minimizing the least square error or using the maximum likelihood, which is categorized as frequentist methods and which we have already seen in previous sessions. However, in Bayesian learning, we are not satisfied with a single point estimation. Instead, we want to know the probability distribution of the unknown model parameters. So guys, in Bayesian learning, we consider each observation y as probability distribution in order to model the both observed value and the noise of the observation. Now let's assume that each observation y is distributed normally as shown on screen in equation 2. Here we have defined that each observation yi follows a normal distribution with mean and variance. Now, let's try to understand the meaning of these mean and variance in terms of linear regression model. So guys, we know that mean of a normal distribution is the most probable value for that random variable. However, according to the linear regression equation, we believe that wx plus tau is the most probable value for y. Therefore, we can define mean as wx plus tau as shown on the screen. Even though mean is the most probable value for yi can also include some error or noise, and accordingly, we model such error in the observations by adjusting the variance term to compensate for the deviations of yi from mean. Let's denote the error term E by using a normal distribution with a zero mean and variance, as you can see in equation 4. So guys, if we add a constant mean to normal distribution as shown by figure 4 or by equation 4, we get a normal distribution with a mean and variance, which is the likelihood of the observation y. Now, you should be able to understand how each term in traditional linear regression model, what we have seen earlier, is represented using the normal distribution as shown in equation 5. Even if we think for a moment, the mean and the variance of a normal distribution represent the most significant value, and the deviation of the values from that most significant value respectively. Moreover, the values nearby the mean will have a higher chance of appearing, whereas the probability of observing the value reduces when moving away from the mean. Therefore, our assumption to choose a normal distribution to represent the random variable yi is not an arbitrary decision. It is chosen such that we can represent the relationship between the dependent variable yi and independent variable xi with the effect of the error term ei using the properties of normal distribution. So once we define the linear regression model using notation shown in equation 5, we get three unknowns: w, tau and variance. In Bayesian learning, these unknowns are also called as hidden or latent variables because we haven't seen values of those variables yet. Therefore, we have to determine the parameters w, tau and variance using Bayesian inference given the x and y. So guys, we can represent such relationship between random variables using the conditional probability distribution such that P of w, tau, variance given that y and x. So if we apply the Bayes theorem to probability of w, tau, variance given that y and x, we get following expression as shown on the screen in equation 6. So we are trying to determine the parameters of linear regression model, and therefore we can rewrite the equation 6 specific to linear regression model. Just to add one thing, that we have omitted the evidence P of y given x in the following equation as of now in order to simplify the equation. Assuming that w, tau, standard deviation and observations yi are conditionally independent to each other, and by knowing this, we can rewrite the last equation for n data points as probability of w, tau, standard deviation given y and x almost equal to pi of each point of probability of yi given wx plus tau and standard deviation multiply by individual probability of w, tau and standard deviation terms as shown in equation 8. So guys, if we can determine the posterior distributions of hidden variables, then we can determine the values for those parameters with a certain confidence. But for that, first we have to define the prior probability distribution for those unknown parameters. So guys, if you can see the equation 9, we have chosen the shape of the probability distribution for w and tau to be normally distributed, and we have given standard deviation the half Cauchy distribution. So now one could say that this is our prior belief regarding those parameters. Actually, we have no way of deciding the perfect distribution to represent our prior belief for this case. Yet, we assume that those random variables can be modeled using the normal distribution. So guys, mean 1, standard deviation 1, mean 2, standard deviation 2, and beta are the hyperparameters to this model, which are also considered as a part of prior belief. Even though it is difficult to determine the shape of the unknown model parameters, we can still guess reasonable values for some of the mentioned hyperparameters. Since we have defined the prior probability distributions, now it is time to define the likelihood of the model. So guys, the likelihood of linear regression model is the probability of yi given wx plus tau and standard deviation. We have already defined yi in terms of w, tau and standard deviation in equation 5. Therefore, the likelihood is given by equation 10 as shown on the screen. Now, as we have defined all the components of linear regression model using random variables with the probability distributions, let's rewrite the posterior distribution using the likelihood and prior distributions that we have defined so far. So guys, this is the complete equation for Bayesian approach. So guys, I have solved this equation for you and want to show you the visualization of hyperparameters what we have seen so far. So by seeing this visualization, we can observe that instead of exact point estimations, now we have probability distribution for each model parameter. Even though we started with normal priors for hidden parameter w and tau, the posterior distributions have a different shape. However, we used a half Cauchy prior for the standard deviation, yet the posterior distribution of that is closer to the normal distribution. Therefore, even with the poor choice of priors, we can achieve accurate posteriors if sufficient data or evidence is not available. So guys, here you can notice the change of standard deviation from n equal to 10 to n equal to 100. However, it should be noted that poor priors should be avoided since they could affect the accuracy of the model significantly in the absence of sufficient data. So guys, furthermore, if we have fairly accurate priors, we can achieve better results even with a fewer data. Whereas frequentist method lead to overfitting of models with fewer data. And moreover, with more data, the slope and the intercepts are getting closer to the real value. So guys, here we can see the confidence of estimated parameters is increased if we compare the width of curves when n is equal to 10 and when n is equal to 100. So we can say now that when more information is provided to learn, the parameter confidence does increase. And here we can see multiple regression lines that were plotted using the samples extracted from such posterior distribution for dataset. And guys, here I am trying to show you the best fit line visualization that we have generated through Bayesian approach. So each black line corresponds to a single pair from both W and tau that was sampled from their estimated posterior distributions. And green line is the true regression line. So guys, when we have less data, suppose for n is equal to 10, the regression lines inferred using Bayesian learning are widely spread due to the high uncertainty of the model, whereas the regression line are well pegged together closely to the true regression line when we have provided more information and say when n is equal to 100 to train the model. Thank you guys for your time. Do like, share and subscribe. Hit the bell icon to get the latest updates. Happy learning and stay safe.